everyone, Mr. Elliott here, and we are continuing our Module 11 with Lesson 4. So let's get into it. Remember, Module 11, States of Matter. We are doing Lesson 4, which is on phase changes. So changes of matter from like solid to liquid to gas. So what causes a substance to change phases? That is our focus question today. Here are some new vocabulary words. Many of them you probably already recognize, so go ahead and pause the video, write those down. All right, so let's get into this. Phase change. A phase change is a change from one state of matter to another. So we're, like I said, going from solid to liquid to a gas. And what we're looking at here is what's called a heating curve of water at 1 atmosphere of pressure. So at 1 atmosphere of pressure, water will boil at 100 degrees Celsius and it'll melt at 0 degrees Celsius. So we're looking at this graph here. We have a heat added down here. So as we add heat, let's say that we start with solid ice down here at 30 degrees Celsius. As we add heat, we're going to heat that ice up until it hits 0 degrees Celsius. At 0 degrees Celsius, you see the temperature. So on the y-axis, we're looking at temperature in Celsius. You'll notice that the temperature actually flatlines right at 0 degrees Celsius. So during this amount of time, all of the energy that is added to the water molecules is going into melting the water. Okay, so it's going into separating. So we got water molecules here and they're in a solid, they're kind of shaking like this. And so at that melting point, what's happening is all the energy is going into separating them into a liquid. Okay, down here during the solid state, during this solid section down here, what you're doing is you have the solid particles and they're just jiggling in place, and as you heat them up, they just move faster and faster and faster. Okay, they're increasing in kinetic energy. And we know that because, remember from a previous lesson, the average kinetic energy of the particles is the temperature. Okay, so temperature is a measure of the average kinetic energy of those particles. So if our temperature is increasing, we're increasing the average kinetic energy, which is the energy of movement. Okay, during the phase change, we are not increasing the speed of the particle, okay, the average kinetic energy of the particle, but we are changing the state of matter. So we're separating those intermolecular forces a little bit more and turning it into a liquid. So then here you have a liquid, and again, during the liquid state, we can heat the liquid up and we can continue to heat it up. So now this is a liquid, those particles are moving around each other. As we heat it up, they just move faster and faster and faster. And then you get to 100 degrees Celsius, where those begin to evaporate or vaporize into a gas. And so now you are fully separating the intermolecular forces, and those particles are now flying around as a gas. And then you can imagine if we captured that gas, we could continue to heat that gas up to higher and higher temperatures. Okay, and so those are basic, that's kind of a basic rundown on phase changes. And so what is actually causing the phase change? Okay, well, that's energy. So when energy is added or removed from a system, we're going to have a change in the phase or a change in state. Okay, previously I talked about, during this graph, we were talking about heating up the water. Well, what happens if we cool it down? Just the opposite, right? So if we started a gas and we start cooling this gas down, it's going to go down and then it's going to condense into a liquid, and then we're going to cool the liquid down and it's eventually going to freeze, and then we're going to have solid ice again. Okay, so we could go backwards as well. So what causes the phase change? Well, adding or removing energy. Okay, so let's look at A over here. So what's this called? So we're going from a gas to a liquid. So that one would be condensation. So we're going from a gas to a liquid, it condenses down. All right, so if we're going the other way, liquid to a gas, what's that called? So that's called vaporization, or you could have said evaporation would have worked as well. Okay, look at letter C. Letter C, we're going from a solid to a liquid. Solid to a liquid. That would be melting. What if we go from a liquid to a solid? That would be freezing. If we go from a solid to a gas, these ones are hard. Okay, solid to a gas, that would be sublimation. And from a gas to a solid, that would be deposition. All right, sublimation, you may be familiar with. That's what dry ice does. Goes straight from a solid to a gas. It's called dry ice because it's what it is it's frozen carbon dioxide gas. Okay, in a white chunk, and I have a picture of it later on in the slides here. So during sublimation, it bypasses the liquid state, and that's why we refer to it as dry ice, because it doesn't get wet. Oh, I know now. You're going to ask me, is water wet? And blah, blah, blah. All right, anyway, so continuing on. Deposition. Deposition you are also familiar with, you just may not know it. Deposition is where, you know, on those cold mornings when you go outside, back when we used to drive places, you go outside and you can scrape the window, or you'd have to scrape the window. What that is that's deposition. So water vapor in the atmosphere has deposited onto your windshield and turned into a solid. Okay, so those are your basic phase changes. Now, these next few slides, I'm not going to spend a ton of time on those, but those are just basically longer definitions of the different phase changes that we just talked about. Okay, and I will post these slides on Canvas so you can get these, or you could pause the video and write these down. All right, so now when there's an actual phase change that occurs, we need to realize that it doesn't all happen at the same time. Okay, so in this case here, we have an energy distribution of molecules in a liquid. Okay, now remember that temperature is the average kinetic energy of the particles. So average kinetic energy of the particles means that not every particle has to be at that specific amount of energy. So in English, what does that mean? That means that at a given temperature, there's some particles that are moving very slow, and there's some particles that are moving very fast. But on average, they have, but all those particles together have an overall average amount of kinetic energy to them, and that is what we measure as our temperature. So if we were to look at the actual distribution of those particles, it would look like this. So here is a scale of kinetic energy along the x-axis. So there's no real numbers here, but we can imagine we got 0 kinetic energy down here, and then it just increases as we go across. Down here we have a 0 number of atoms, and then the number of atoms at that given kinetic energy increases as well. Okay, so way down here, low kinetic energy, so moving very, very slow, we have very few molecules. As we increase kinetic energy, we can see that we're increasing the number of molecules. Okay, and so then it peaks here. And then as we continue on, lost my mouse. As we continue on, we can see that as we get higher and higher in kinetic energy, we're getting fewer and fewer molecules that have that amount of kinetic energy. Okay, so let's say, for example, actually, let's do this. Let's say that we do have our glass of water just sitting here. Okay, so I have my glass of water sitting here, and so right now my glass of water is at some temperature. Okay, let's see if there we go. So I have my glass of water at some temperature. So some of those particles in that glass of water are down here. Most of the particles have this amount of kinetic energy. So our average kinetic energy is probably going to be somewhere in this region. Okay, but some particles, very few particles, but there are some particles have a really high kinetic energy here. And those particles with that kinetic energy have the amount of energy, the actual amount of kinetic energy required to vaporize. So what that means is that even though I have this cold glass of water sitting in front of me, there are some particles that do actually have the amount of energy required to turn into a vapor. And that is why if I leave this glass of water here, it will eventually evaporate, because there's always some particles in there that have that amount of kinetic energy to turn into a gas. Okay, so that's what that graph means there. Also means that when we are boiling water, so here's a tea kettle, and we're boiling some water. So we reach 100 degrees Celsius. Why doesn't all the water just disappear? Well, that's because most of the water still is not at the required amount of energy to evaporate. But the water that's inside those bubbles has reached that amount of kinetic energy to turn into a gas. Okay, so here's some more information about evaporation. Again, you can pause, write this down, or I will also be posting the slides later on. Okay, and then some more information about boiling. Boiling's kind of tough. This one, if you really want to get into it, I would encourage you to look on Google, look up some more videos and things like that. The temperature at which, so boiling is technically the temperature at which the vapor pressure of the liquid is equal to the external atmospheric pressure. So then we have to get into vapor pressure and all that stuff. I'm not going to get into it here because we're running out of time, but go ahead and explore that. Go ahead and explore online about vapor pressure and boiling point. Okay, sublimation. Like I said, sublimation is what carbon dioxide does. So here's dry ice, here's solid carbon dioxide, and it's just going to go straight to a gas and bypass the liquid state. Freezing. So freezing point, again, pause the video, write this down. And condensation. Okay, deposition. Remember, deposition's where we're going from a solid, or sorry, we're going from a gas, and it is going straight to a solid. Okay, the final thing I want to talk about is phase diagrams. And in phase diagrams, they look like this. Phase diagram shows us the pressure versus temperature. Let me get my face out of the way here. Pressure versus temperature. And so we can see, let me actually, yeah. So as we're increasing temperature, and how does that compare to the different pressures? And it will actually tell us at any given temperature and any given pressure, it'll tell us what state of matter we should have for that material. And you can see this is the phase diagram for water. So what that means is that every substance has its own phase diagram. So methane gas, will have a different phase diagram than water will. And you'll notice that kind of the three different phases, they all meet at the triple point. Okay, and the triple point is where all three states of matter can coexist. And this is a really tough thing to kind of think about or visualize. But it's that magical moment or temperature and pressure at where all three of them will kind of coexist, and they're all kind of going back and forth between, like the water molecules are going back and forth between all the different states of matter. Okay, so here's just kind of a bigger picture of, so if we take 1 atmosphere of pressure and we go across, if we start here down below a temperature of 0, we're going to have a solid, and then we hit the melting point, and then it melts into a liquid, and we heat that up, keep heating it up, and we hit the boiling point, which then we turn into vapor. And so that's how you would read that. So if we wanted to change the pressure to 217.75 for whatever reason, atmospheres, we'd have a solid, and then it would turn into a liquid, and it would stay a liquid until it got over here and reached the gas phase. Okay, so as I mentioned earlier, the triple point is where the three states of matter can coexist. And so I have this quick little video here. What we got is we have a little evaporating dish with water inside of it and ice water. And it's inside of a vacuum chamber. So they had some water, liquid water in there with some ice in there, and they put it in a vacuum chamber. Let's see if this works. So right here, what they did was, as they lower the pressure, they're now at the triple point. And if you look really close, you can kind of see, watch the bubbles. The bubbles look like they're kind of getting trapped in the, so let's back up here. The bubbles kind of look like they're getting trapped inside the liquid, okay? And so that liquid is kind of going, it can't decide if you think about it from the liquid can't decide if it's going into a solid state or if it's going to go in a gas state, okay? And so they're kind of going all over the place. So really we have all three of those states of matter occurring at the same time. It's kind of cool. Found this video on YouTube from University of California, Santa Cruz. So the other thing that you see in here is the critical point. So what is the critical point? The critical point is kind of interesting. That's a point where if you go past, you'll notice this line actually stops at the critical point, and then they of course continue the shading on here. But really what's happening is beyond this point, both of the liquid state and the gaseous state, they have the same density and are really indistinguishable from each other, which is kind of a bizarre concept to think about. Like I mentioned before, each my face is in the way. Each material has its own phase diagram. So over here we have CO2, and so here you'd have dry ice, you'd have solid CO2. At 1 atmosphere of pressure, you can see that it goes from solid CO2, so that solid dry ice, and then all of a sudden at negative 78 degrees Celsius is going to naturally want to turn into a gas. Now if we raise the pressure up a little bit, so raise the pressure up, and we come across, we start heating it up, we could actually get liquid CO2, and then and that's what would be in like a CO2 tank that's hooked up to a soda machine at like a fast food restaurant or something like that. All right, so over here we have carbon, and as you can see here, we have here's 10 atmospheres. So this little dot kind of represents about 1 atmosphere, about where we're at. So 10 times the pressure that we're under right now, this is where it would be here. So you can imagine it'll go way up here. There's about 1,000,000 times or 1,000,000 atmospheres. We can get diamonds. And diamonds and graphite, those are both solids for carbon. And those are allotropes, if you remember from lesson 3. And then we could actually get liquid carbon if we had a high enough pressure and high enough temperature, and then you could actually vaporize carbon as well. So at 1 atmosphere of pressure, if we heated that carbon up, we would not melt it, we would actually sublime it into a gas. So let's go ahead and test our knowledge. Which of the following is an exothermic process? Exothermic, exo means exit, and thermic means heat. So the system is losing heat in an exothermic process. Okay, so go ahead and see if you can answer this question. Okay, so if it's exothermic and it's losing heat, let's think about that. So we have our glass of water here. If I wanted to boil this water, I have to heat it up. So I have to add heat into this water. If I wanted to freeze this water, I need to put it in the freezer and cool it down. When you cool something down, you're pulling energy out of it. So that is an exothermic process. So freezing is an exothermic process. This particular question is looking for what is not an exothermic process. So freezing is exothermic. Condensation is going from a gas down to a liquid, so it's cooling down. Sublimation, you're going from a solid straight into a gas. So solids at low energy, gases are at really high energy. So that would mean that it has to gain energy to get there. and that would be your answer. All right, number 2, what is the term for the process by which a substance changes from a gas to a solid without first becoming a liquid? Five, 4, 3, 2, 1. Deposition. Toughies. All right, number 3. Which phase changes require energy? All right, which phase changes require energy? Okay, melting, vaporization, and sublimation all require us to put energy into them. All right, which of the following is the reverse of vaporization? So opposite direction of vaporization will be condensation. Alrighty, I hope you enjoyed Module 11, and we will see you in the future.